Hi, and welcome to this month's live session. Today, we'll talk about this phenomena of ChatGPT, how it came to be, and how it was revolutionary in its own way. A little bit about how it works. I'll try to break down most of the terminology surrounding it and give a general purview of the very complicated world that eventually led to the reality we now see. And then, towards the end, a little bit about its shortcomings and the path forward. So, welcome to the journey to ChatGPT. A little bit about myself before we begin. My name is Rishita Bapuram. I'm currently a master's student at University College Dublin in Ireland, where I'm studying data and computational science, and I have a background in applied statistics. I'm also an AI educator with Coding and More, which has by far been a very rewarding experience for me, and also the reason why I'm here on this session today with you all. With that, let us first start with what ChatGPT really is and what makes it unique. So, ChatGPT, as we all know, was developed by this company called OpenAI. Their prototype, generative, pre trained transformer, that's where the GPT comes from, was released towards the end of 2022. And it's a type of what we call a large language model. We'll come back to these big words one by one shortly. But what sets this apart from those tiny chatbot icons that we used to seeing in most websites is that it uses advanced artificial intelligence and machine learning techniques to generate almost human like responses, which makes it both personalizable and convenient, right? And since it was trained on a massive corpus of data, it feels like it pretty much knows everything. And while it saves us the time, it used to take for us to look things up on Google and then find specific web pages to point to the answers. Instead, today on ChatGPT, you can just type a question and it will either you can ask it for reference links or it'll even summarize articles for you and save time. Also, most of the traditional chatbots that I speak of here are not intelligent per se, since they're usually a glorified FAQ function, right? They have a set of prompts and responses. So, depending on any question that you type, it'll look for certain keywords that it identifies as prompts and it would match it to potential answers and present them to you. And in a situation where those prompts don't exist or those keywords don't match, it will just lead you to something like giving your contact details. And then at the end of the day, you'd have a human consultant who would call you back. Um, yeah, and those were the traditional chatbots, usually a more interactive FAQ functionality. But the leap didn't directly happen from there to ChatGPT, right? There were a lot of ideations, there was a lot of research done in the process. And I believe the earliest of the smarter chatbots were way back in the 1960s and the 1990s. That was Eliza and Alice. Which aimed at mimicking human conversational behavior, the way we speak and patterns in speech, which is almost exactly what ChatGPT does even today, but definitely in a more robust, in a much, much larger scale, and definitely in a more efficient manner. Which is why it gained almost the overnight popularity, right? If you see in this slide, the graph shows the Google search trends worldwide about ChatGPT and AI, which kind of blew up in December of 2022. And the yellow line here, which is the popularity of the new Google's Bard, which is still yet to grow since it's only been out for a few weeks now. In fact, in India, if you come to this table here, over the last 12 months, the popularity of this topic increased by nearly 3,700%. And I pulled these stats out of Google Trends yesterday, so IPL, of course, is still the hot news. But otherwise, you'd see that GPT has been the main topic of discussion over the internet, right from explaining it, people teaching you how to use it. In fact, there are a whole bunch of courses that have come out now that teach you what kind of prompts you should do. You should ask in order to get accurate and better responses. It's called prompt engineering. And also, perhaps the biggest source of misinformation, because there are a lot of people who are also talking about what it can do, the number of jobs it can take away, this and that, and a whole range of things. And the last graph here is from a website called SimilarWeb, and it shows the month-on-month increase in the number of people using the chat.openai. So that essentially opens up the chat window where you can interact with ChatGPT. And as you can see, it quickly grew from 1 billion users in Feb to almost 1.8 billion users in just over 3 months. So I think it's safe to conclude that ChatGPT and its aligned technology in generative AI and large language models are here to stay. So knowing about how they fundamentally function is of prime importance since they're becoming a part of nearly everything. Perhaps in a decade or so, it can even be a part of our justice system and has a very direct impact on how we will lead our lives, which is why this discussion surrounding how it works and even understanding the general structure behind it is of very high importance. So before we begin to understand the architecture and the working of these really complicated models, there are some terms that we'll keep coming back to, and I thought it'd be best if we discussed some of them ahead of time and the rest as we go along the journey. These two mind maps are always my go-to because they pretty much summarize the entire world of data science in them. First up, artificial intelligence. We can think of this as the ability of machines to program, to think, and make decisions in the same way that humans do. Machine learning is a part of AI that is again comprised of a large variety of methods to construct this decision making mechanism, right? And essentially, what we do is try to build models which are able to summarize or represent it in a way that the pattern of certain, in order to account for certain behavioral patterns in the data. And this model is constructed in a manner that it would also enable us to predict future tendencies as well with a fair level of certainty. So this can happen in many ways. As you can see in the mind map here on the right, on the left. In the respect of time, I will not delve deeper into each of the four categories here, but our discussion today will mostly surround neural networks and deep learning, and also a little bit of reinforcement learning, because that's primarily what ChatGPT uses. Additionally, it is also important for us to solidify our understanding of models because that's fundamentally what when we come to large language models, if you don't understand what a model is, there's no point in me explaining the other prefixes to it. So, what models are, they essentially aim to simplify complex phenomena or data in much easier formats. For example, suppose I was trying to understand how much money I would spend depending on how much money how much money I've earned, right? I would be trying to predict the relationship between my income and my expenditure. So here, suppose I say I had some 20,000 data points about my expenditure when my income is at different levels. So 200 rupees, 5,000 rupees, 20,000 rupees, 600, 700, and so on. It would be hard for me to summarize so much information in one go with just the data, right? Because I have 20,000 data points. If I had a model, however, it would allow me to build a formula of sort, which would tell me what my likely expenses are going to be using the amount of income that I have. And this is excellent because it allows me to capture the information that all those 20,000 data points are giving me. And at the same time, it will also give me the flexibility to predict what my future expenses could be like, depending on any level of income that I set. Similarly, we can also construct a simpler version of the human language. So any language, English that we speak, can be simplified in a simpler format. That's a model. And that's where language models come in. And in large language models, the large simply implies that there is a large amount of data that is used to train it. So any model with a large amount of data implies that it requires a large amount of space to store it, and that's why we call it large language models. What are neural networks? Neural networks are one of the approaches to construct the models we just discussed, right? The main idea is to approach learning from the data in the same way that the neurons in our brain do, using electrical impulses and connections. So in a general neural network, you'd have a set of inputs that pass through a set of what we call hidden layers, and then they would give you your desired outputs in any format that you would expect to see them in. Let's understand that better with an example. Sorry. So as you can see on the slide, we have the task of recognizing which number is written in the written text represents. Here you have two different images of 9, right? This is actually a very classic example of neural networks, which is handwriting recognition, perhaps also one of the earliest uses of neural networks. Now, what happens in this image now is, I know it's blurred, but it's divided into a grid of pixels. So 28 by 28 grid. So that gives you a total of 784 pixels. And all 784 of them would be your inputs. And what those inputs would be that would tell me what percentage of white color is present in each of those pixels. So I have pixels towards the edges here that have 100% black. So right, 0 would be their value. Whereas somewhere in middle, I have pixels that are completely white. So that would be 100% white. And there are pixels that are partially white as well. So now what happens is, in each of the layers between the input and the output, so these are called the hidden layers. Here we have two of them, right? We filter out for what we consider to be important pixels and their positions. For example, in this case, I would only think about the pixels that are completely white in my first hidden layer. So that would tell me which are the regions that are very, very important for the shape of this number. And in the second one, maybe I'd also check for the ones that are partially white. So that will enable me to understand if there's any shape to the numbers. So I would understand if there are any circles like in 0, 6, 8, or if they're just straight lines like in 1 and 7, or maybe a mixture of both as well, like in 3 and 5. And from there, I would be using the information to predict the probability of the image being each number. So I would assign a probability to that image being 0, for it to be 1, for it to be 2, 3, so on till 9. Now, in this case, I would imagine that if my model is working properly, I would expect to get the highest probability for the value of 9. And then I would predict that the image to be 9 because it has the highest probability. And that's why here in this GIF, you'd see that the 9 at the end gets highlighted. So that's the basic idea of how a neural network flows. Now, how each neuron in each layer gets activated is a complicated mathematical process. I will not get into too much detail of it, but we'll try to understand that in a simplified format of how that procedure of back and forth works. So for this, I borrowed an example from an amazing article written by a professor called Mark Riedel from Georgia Tech on the same topic. And I would highly recommend that everyone read it at some point, especially if you're a beginner in this field. His analogies are quite good. Okay, so imagine that you've built a self-driving car that can navigate highways. Right. So in order for it to understand its surroundings, you've equipped it with proximity sensors. And what proximity sensors do is they would tell if on any side that they're placed in, if there's any object closer to it. So ideally understanding if something is in close proximity. And you've equipped it with proximity sensors in all four sides of its body. And robotic mechanisms. So what robotic mechanisms here are the controls on your accelerator, brakes, and your steering wheel. So your steering wheel controls the direction your car turns in, your accelerator the speed, and the brakes when it will stop. But now you have a challenge. You've connected, how would you connect these sensors to those four robotic controls to ensure that your car is taking the information from these sensors, using that, and then making those decisions of whether to increase the speed, reduce the speed, put a brake or change the direction of the steering and so on. So at first you might think that connecting each sensor to every part of the car is the way to go, right? But when you try it, the car goes crazy. So it turns left and right, it accelerates, it brakes all at the same time, and it's a big mess. So you need to come up with a smarter way to do this, right? So this is where we introduce something called resistors into the car system. Now, what resistors are, they help you control the flow of electricity between the sensors and the different parts of the car. For simplicity, you can think of them sort of like the controls of fan speed on our walls. Except here, you would decide how much electricity flows through that particular wire. So we place them in specific spots to make sure that the right amount of electricity goes through each part. For example, we want more electricity to go to the brakes when the sensors are in the front and they detect something close, because that's important. If there's something in front of me, then I'd want my car to stop and not make any other decision. Therefore, you'd want more electricity to flow there. and less electricity to go to the steering, because I don't want it to turn when there's something in front, right? And hence you would need the car to stop if the sensors in the front detected something. Now, we could also use something called gates in the circuit. And what they do is that they ensure that they would open the flow of electricity only when a certain amount of electricity is accumulated at that particular point. So, for example, we might have a gate that only lets electricity go through when both the front and the back sensors detect something close, right? And another gate might send some more electricity to the accelerator when the front sensor detects something that's very far apart, or it says, okay, the path is clear. So you would want the accelerator to speed up there. And when that happens, here in the image, you'd see that the thicker lines mean that more electricity can go through them, and the thinner ones, less electricity. And these circles that you see in between are your gates. So they're ensuring that there's a fixed amount of electricity reaches before you move on to the next stage. So now what happens when we run the car this time? You'd expect that it do a much smarter job at navigating the vehicle in turns, right? And so it takes your turns, your stops, and it speeds appropriately. But where do we put these resistors and gates? At first, we don't know. So we try out different combinations, and this is where the math comes in. So we randomly add and adjust them to see what happens. Sometimes the car behaves correctly, but sometimes it doesn't. So take some trial and error to find the best arrangement. But that feels like it's a very um, primitive way to approach that, right? So, luckily for us, there is an algorithm that Professor Geoffrey Hilton and a whole bunch of others came up with many, many years ago called backpropagation that helps us improve. Now, it looks at how the car behaves and makes small adjustments to the resistors and gates just to make it better. So it does this over and over, making tiny changes each time until the car starts driving more like we would want it to. And we call these resistors and these gates and their appropriate settings as our parameters, because it is usually it's actually they're everywhere. And what the backpropagation algorithm is doing is declaring that each resistor is stronger or weak. Thus the entire circuit can be reproduced in other cars if we knew these settings of these resistors and these gates and their particular values. Now, deep learning is just an extension of this concept, but it just implies that you have a much deeper network, in the sense that you would have more hidden layers or neurons to be able to explain some more level of complexity in the data set. Okay. Now, have you ever thought about whether a machine could generate sentences that resemble what humans write? That's precisely what we're trying to achieve in creating a circuit that can predict the right words to output based on a series of input words using their conditional probabilities. Now, when I mention conditional probabilities, it should take you back to 7th, 8th grade mathematics, where you learned something called the Bayes theorem, right? So I'm trying to predict the probability of something happening, knowing that something has already happened. So you would say that, okay, I am tossing the coin twice. But I already know that the first time I got a head. So what is the probability that I'll get a head again? In this case, it would be independent, right? Because if I tossed it once, it wouldn't affect the other. But generally, when you have related events, for example, if it rained yesterday, it's more likely that it might rain today if it's the same season, right? So that knowing that it rained yesterday would help me give a more accurate answer of whether or not it's going to rain today. And that's where conditional probability as an idea comes in. But let's take a step back and try to simplify it a little bit more in terms of a language model. Now, imagine you have a massive keyboard, much larger than the regular ones that we use on our laptops and our PCs. But here, instead of each key being a letter or a number or a symbol, imagine that it's each word of the entire English language. So assume that there are some 50,000 words, and this keyboard has 50,000 keys, with each key corresponding to each word, right? So, and when they're connected to that output mechanism, it's a very, very big circuit of 50,000 keys, one for each output. So similarly, we would have 50,000 sensors, each for one detecting the presence or absence of that particular key in any sentence that you're looking at. So ultimately, our objective, as you can see in this image here, is to identify the key that receives the strongest signal, indicating that the most probable word to complete the sentence. So what we're essentially doing here is selecting the right word based on the highest electrical activity. Suppose I had a sentence. For example, I have a sentence here that says once upon a dash. Now, if I had a word like, let's say, king, once upon a king does not seem that likely, right? But once upon a time sounds extremely likely. So that would have the highest electrical impulse. And that's the logic. So you're looking at the conditional probability of me including the word time in the sentence, given that I have these three words already in the sentence. And that is the primal fundamental idea of how language models work. So ultimately, our objective here is to identify the key that receives the strongest signal, indicating the most probable word to complete the sentence. However, here's where it gets challenging. If we want a circuit that takes one word as input and produces one word as output, we would need 50,000 sensors for each word and 50,000 outputs, one for each key. And that would be around 2.5 billion connections in total, right? That I'd have to understand where to control each of those 2.5 billion connections. But here's where it gets more complicated. Now, I don't have a sentence with just two words, right? I have multiple words. Suppose I want to fill in the blank for the sentence that we just discussed. So, once upon a. So, here by identifying the word for each of the three input positions. In this case, we would require 50,000 into three because I have three words. That would be 150,000 sensors. And then we need to connect them to 50,000 other words. So 50,000 keys. Now, how many connections would that be, right? So that would be 150,000 multiplied by 50,000, which is 7.5 billion connections. And now, just to put that into perspective of how our modern computers work today, in 2023, most of the largest language models can handle only around 4,000 to 32,000 words at once. So now that's a level of complexity that we're not able to handle today. So now we need to address this situation in a very, very efficient manner. So we need to employ clever techniques and strategies to manage it effectively. So what we'll do is break down the problem into smaller stages and tackle them step by step. Ideally, you'd split it into two different circuits. Step one is encoders. Now consider these phrases here. The king sat on the dash, the queen sat on the dash, the princess sat on the dash, and the regent sat on the dash. Now, what would you guess would fill the blank the most? The most likely you'd say either a throne or, well, say toilet, right? The interesting thing here is like these words, king, queen, princess, and regent, all have a very common theme. They all represent people of royalty. So instead of having separate connections between each word and the word ultimately throne, which is very likely, I could just simplify it to say royalty. If there is a word that implies royalty, then that blank would be throne, most likely. So our idea here is to create an intermediate or temporary representation of sort that captures this concept of royalty, that essentially clubs the common themes between these 50,000 words. So we'll set up a circuit with those 50,000 word sensors. That's what we start with. But instead of mapping them directly to each of those 50,000 words, we would create a smaller network of, let's say, 256 outputs. And these combination of outputs explain different concepts. So you could have royalty, mammals, birds, food, things like that. So general, like sort of like an umbrella that would include any words that fall into that category. So also each of these outputs will have a range of values. It's like each output has a different amount of force with which it can activate. So we can express shades of similarity and strength between words through how big the output value is. So previously, in the first example that we discussed where we needed 2.5 and 7.5 billion connections, we would need a separate sensor for each word, which would result in 50,000 individual connections. But now we've condensed those 50,000 sensors to just 256 sensors, and that's an encoding. For example, the word king might be represented with, vector of different values. You have 0.10, 0.9, so on, 256 values. And then queen could also have a whole set of different values. And these encodings capture the similarity between the words. So I would look at the values, and if the values are similar, then I'd say, okay, these two words are quite similar to each other. And we call them encodings because they represent the hidden state or any underlying similarity or meaning between these words. So ideally, what I'm doing is I'm trying to club them together, right? I'm saying, okay, these three words are similar, those five words are similar, these whole set of words are similar to each other. So I'm attaching labels of sort that will enable me to group them together. Okay, now I have encoded words. Step two is decoders. But the encoder does not tell us which word should come next in the blank, right? So we need to pair our encoder with a decoder network. Now, what's a decoder network? It's another circuit that takes these 256 encoded outputs as my input, and then they take up the job to activate those original 50,000 words that we have. So it's our job to take those compressed encodings, those 256 numbers, and decode them back into words. So it's like unzipping a compressed text and then restoring it to its original form, right? We would then pick the word with the highest electrical output. Again, the highest probability there. Like you can see in the image where it says, you have some encoding that's leading to the word upon. Okay. Now it's truly fascinating how these encoder and decoder networks work together. So it's much like a compression program, right? So they allow us to represent a large number of words with a smaller set of numbers, like making language processing more efficient and manageable, right? Instead of me having those 2.5, 7.5 billion connections, now it's just reduced to a very small number. I'm first mapping them to 256 encodings, and then I'm just decoding those to give me the highest probable word. Okay. Now let's start with a small thought experiment, right? Now imagine I have an encoder decoder network that we just discussed, and it takes a single word and it produces the exact same word as output. So if I start with king, I want my network to give me king as the output. I know it's silly and it does not make sense, but it helps us understand this process better. So stick with me. Okay, now let's say that the word king is into the network. Like I said, the encoder receives the electrical signal from a single sensor and it activates something in the middle. That's the encoding stage. And if everything is perfect, the decoder should give me the word king, right? With the highest electrical signal. Now it sounds simple, right? Well, not quite. Here's the tricky part. It's equally likely for the decoder to produce the word armadillo with the highest activation energy instead of king. The difference between the expected output of one and the actual output is what we call the error or the loss. Now, we can use this technique that we discussed before called backpropagation to make these adjustments to the decoder and the encoder to ensure that slightly different encoding is generated so that we encode the word either that's king or that's very similar to king. Now, the process is repeated for all the words in the language. And since the encoder has only 256 values to represent 50,000 words, it will make some errors in between. You're making a compromise, right? You're letting go of some information about the data. So some words will end up sharing similar combinations of activation energy that we call in the encoding process. Now, for example, it would be beneficial for the encoder to make the encodings for king and queen nearly identical because it means the same. But then king and some word like armadillo are so different from each other. So this allows the decoder to have a better chance at guessing the words based on the 256 encoding values. So essentially what's happening is if the decoder sees a particular combination of encoding values, right? So it assigns, let's say it assigns a slightly higher value to king or in comparison to queen, that's still acceptable. But that's as long as king and queen both are higher up there, in the sense that I would penalize my decoder if it prefers king and armadillo together more than when it would pair king and queen together because they're more similar than king and armadillo. It's a fascinating process so that allows language models to generate more and more accurate connections. And in a way, it also helps the model understand the meaning of a sentence. So it understands the underlying structure to things. Okay. Continuing further, now, have you ever played a guessing game? So imagine playing a game where you have a sentence with one word missing and you have to guess what the next word could be. Now we're going to use a very similar idea to build something called masked language models. In a masked language model, we give the network a sequence of words and then we ask it to generate another sequence of words. But here's the twist. We blank out one word, one of the words in the input, and the output sequences, and that's represented by the word, essentially the mask. So the black portion here, the word that's hidden. For example, let's take the sentence, the dash sat on the throne, right? So here in this case, the dash would be my masked word. And the network's job is to guess what the word should go in place of mask. Now, guessing all the unmasked words, right? So the unmasked words would be the, sat on the throne. So now mapping those would be a very simple task. But the interesting part is the ability of the model to guess that masked word. So we try to see how well it can fill in the missing word. Now, to do this, we assign 50,000 possibilities of the entire language to that word. And for each word, the network, it can choose from one of those 50,000 words. We can focus on 50,000 keys specifically only for the masked word. And we move this around the sentence, allowing the network to guess how it would be placed at different positions and how much probability or how well that word would fit in. So, how likely is it that a particular word would be in that sentence? So, I wouldn't say the cat sat on the throne, right? That probability of that sentence is quite low to come up, as opposed to the queen sat on the throne, which is more likely. So, that's how my model would pick the best one. Now, as an extension to this, there's a special type of masked language model called generative masked language model, where we have only the mask at the end of the sentence. So, this is called a generative model because the mask is guessing for so the mask is guessing what comes at the end of each sentence, right? So it's like generating the next word. It's like teaching the computer to build its own sentences. So, depending on all the words that it's used before, it'll try to guess what the next possible word is, and then so on. So, it starts with the. With the, it can be any word, right? So, the possibilities are endless. And then the next word would be the queen. And when the queen comes, again, the possibility of the next few words will reduce, but there's still too many. The queen sat, and then that would slowly narrow down, where my options of what the next word would be would start to slim down, and then I would have a proper sentence in place. So that's what the example here is. So we start with the word the mask, which is a hidden word, and the network tries to fill in the masked word. So it can have anything. So it can guess the cat, the queen, the king, the boy, the girl, whatever. So then the next word, we continue the queen, and then the next word is missing. So now it guesses again. So maybe saying the queen sat, or the queen stood, or the queen spoke, or the queen sang, right? And then we continue again. And it guesses again, saying the queen sat on. The queen sat on the mat. The queen sat on the throne. The queen sat on a ball, whatever it is, right? So it'll assign to probabilities to each of those words, and the most likely one it would pick up. And the network again fills it again once more, saying that the queen sat on the chair or the queen sat on the throne. Now you'd see the throne is probably the most likely word. So then it's a stick to that sentence. So therefore, by using these masked language models, we can train the network to become better at understanding, generating these sequences of words, and learns to make intelligent guesses based on the context and the available options that it has. So, like I said, the options that I have as my sentence gets longer and longer would slim down because there are less and less words that would fit in there appropriately. So it's like a game of fill in the blanks, and I have like a whole set of jumbled sentences, and I'm trying to pick the best one and arranging them together. And over time, and when you have a large number of examples, the network gets really good at it and it becomes quite fast. So, masked language models allow us to generate meaningful sequences of words by predicting the missing words at the end in case of generative ones, based on the context, so based on whatever comes before it. And it's a clever way to teach the network how to understand the generative language more efficiently. So, it's essentially learning how to speak, but not quite so. All right. And that brings us to the three big aspects of what build ChatGPT. So we just discussed generative. It's the ability of the model and it's capable of generating continuations to the provided input. So if I have some input, it's trying to build things forward. So if I have some sequences of words or some word, it will try to attach what is the next possible word along with it, and it'll try to build a sentence that way. That's why it's generating something and it's generative. Therefore, it's a generative model. Pre-trained. Now, this happens when you're training your model to start with on a very large amount of data. Now, there's a whole set of advantages and why it functions in a very efficient manner. It also allows or enables me not to continuously keep training my model over and over again, which makes it very efficient and fast because I already have quite a robust and quite a well trained model even before I start my training process. So that would really keep my model quick and efficient, which is why ChatGPT gives you those results as quickly as it does. Even though, it has access at one go to so much of information, and you'd imagine that it takes some time to look through it. But because it's already trained, it's able to make those connections quite quickly and then construct those sentences forward. Although, in order to make them better, there are small changes that they can make. They're called updates in between. We'll not get into that. That's a whole other field of study. And the last part is a transformer. Again, this is not something that we'll get into, but it is a specific type of the encoder decoder model that we just discussed in a bit of an advanced way, and it optimizes on certain things. So it tries to ideally do that good job. So we discussed that if it does the best job, then it would map my words accurately, right? To give me the best likely words. So the transformer is like a method to do that and so far it's worked out very well for most models. And that's where the generative pre-trained transformer, GPT, and ChatGPT, because it's able to talk to you, comes to be. There's another small thing to ChatGPT that people say makes it very special. It also uses something called reinforcement learning from human feedback. Now, we all have some understanding of what reinforcement learning is, right? If not, it's a kind of machine learning technique where I'm trying to teach. Let's take the example of how you would train a dog, right? Um, if I want to teach my dog to sit, then I would first allow it to sit. And if it does that job correctly, I would give it a treat. So that's a reward. And if it does not, then I wouldn't. I would hide the treat back. So either I would say, no, you did a bad job. So that's like a punishment. And over time, when you do that repetitively, the dog kind of picks up on the cue that, okay, if I sit like this, she's going to give me the treat. So I'm going to do that. So it's learned that action. So the moment I say sit, it'll sit down because it knows that there's a reward coming at the end of it. So reinforcement learning is a very similar idea that you implement into training models. So in case of, let's say, if I'm teaching a robot to do a particular task, if it does something correctly, I would assign something called a reward. So it understands that if it does that job in a particular way, it gets a reward. If it doesn't, then there's a penalty. So ChatGPT employs a very similar idea to ensure that its answers are up to what I would expect it to be, right? So if I suppose I'm asking ChatGPT, okay, ChatGPT, give me the perfect way to make a chocolate brownie. And it's given me a recipe. But I see that something's wrong with it. I see that it's mentioned for me to use something that I don't think I should use. I think that that recipe is wrong and I'm not happy with it. So what I would do is make note of it the next time you open ChatGPT. Many people miss it, is that it has a thumbs up and a thumbs down option at the top, right? So I can say that this answer is something that I like, it's helped me, and I think it's done a good job at giving me answer to the question that I've asked. Or I can say thumbs down, like I'm not happy with this. So the moment I put a thumbs down, it'll be like, oh no, the answer that I've given here is incorrect, or maybe there's something wrong about it. So then it'll go back, it'll be like my connections, there's something that I need to alter there to ensure that the answer that I'm predicting to whatever question I've asked is the most appropriate one. So what happens here is, as I am interacting with ChatGPT over and over again, and I keep giving it this feedback of good job or bad job or whatever it learns my understanding of things and what I would appreciate and what I would call a correct answer and a wrong answer, right? So this helps in many ways also, because if I feel like, if a particular statement that's giving me, if I say, oh, this is a racist statement or this is a biased statement, I would just say thumbs down, and it'll pick up on that. And over time, if many users do it, it would correct that way. So it is a way for you to also contribute towards the training of ChatGPT and making it better. But many people confuse this functionality to be a way for us to say that ChatGPT does a more accurate job. No, what ChatGPT is doing is it's trying to understand your definition of right and wrong. And if a lot of people say this is the right and this is the wrong, it would correct that itself as well. So it's also in a way picking up on our own understanding of right and wrong, which in itself is subjective, right? So there's no way for you to quantify the accuracy of ChatGPT using its reinforcement learning mechanism at least. But so far it's done a good job in enabling it to communicate in our terms better. So it's in many ways this has helped for it to understand our ways of speaking, understand those pattern recognitions, understand, also ensure that we are understanding what it's communicating back to us. If I just say something like, can you explain this to me in a simpler manner? Why is it able to do that? Because it has understood over time that if I use this kind of a language, if I use these words, it's better understanding. But if I use a complicated word, maybe this person will not understand it. So that's the feedback mechanism, and that's why human feedback makes ChatGPT even better. Okay. Now, but what do you have to watch out for? The beautiful thing about the complicated world of this large language models is that because we don't understand how they're built, we tend to assume that it can do so many things. Yes, it is artificial intelligence. Yes, it is capable of doing certain things for you, but it cannot do your math equations for you. It's not built to do that. If you're asking it to add up a sequence of numbers, it does not have a calculator that's doing that operation for you. What it's doing is it's mapping each character in that sequence of that equation you've given it to over its database, trying to see if there is an answer to that, and then just giving it to you. So it's not performing any actions as such, right? So it does not have any core beliefs. It is not built on any computational systems in place. It just is a guesser. It's a word guesser. It is a sequence guesser. And that's all ChatGPT is. It's very important to keep in mind that if you're using it, you should understand that it is not. It does not have a way for it to also know if it's giving you the right answer or wrong answer. To ChatGPT, it's right if it's the most frequently occurring. But you and I both know that a lot of us could make the wrong mistake and it would learn that to be wrong, right? Okay. And because it is trained on the internet, they've used the entire data on the internet to train it. So it is sensitive to all of our remarks, stuff that a lot of us have said together. It will pick up on that. It has our own biases. If we have been discriminative on the internet, if we have made statements that can be offensive, it picks up on that as well. And also our language. So the way we speak, if there's any foul language used a lot, it can pick up on that, although OpenAI has instituted certain filters to avoid that mechanism. So they don't have any core beliefs, like I discussed, and they do not absolutely have any sense of what is truth, right, or wrong. It's a completely subjective idea. And because it is subjective, it cannot pick up on that in terms of our communication, and therefore it has no idea if it's right or wrong. And that's why it can make mistakes. And if you're making any decisions using suggestions that ChatGPT has given to you, you have to be very careful for it with it, right? Suppose I'm trying to buy stocks using what ChatGPT has advised me, that would be a very wrong move to make because a lot of people might have advocated for it. So ChatGPT suggesting it to me, but those people could have made losses, but I have no way of knowing that. Right. So I cannot make risky moves using anything that ChatGPT advises me to do unless I know that to be true. That's why you should verify the outputs of a large language model. And if there's anything that you take away from today's session, it would be this, that the model at the end of the day is just striving to emulate the most common response. If a large number of people in the past have said it, it'll give you the same answer. It is just a word guesser. It is not a computational system. It is not an all you know it robot which can give you any sorts of calculation answers or solution. It is not Jarvis from Iron Man. It's not capable of those tasks. But maybe in the future, we could have integrations with different systems and make it smart like we would expect it to be. But as of today, it is not. And keep that in mind every time you use it. And that brings us to the end of the session. And I would like to leave you with a quote from an article that Supriya Ma'am had shared a while ago, which spoke about the impending threat that people felt, that, creatives and people, copywriters, marketing agencies, poets, writers would all feel threatened by the fact that ChatGPT is here because it's able to do what well, they claim to do. And the quote goes, there is a revolutionary shift in how we look at the tools of creation. It's less about making the act of creation easier and more about how we create in the first place. And that's a beautiful thought, because over time you realize that maybe with the advent of cell phones, right, we've been able to create content in many ways, we've been able to consume content in many ways. That does not mean that every person that you see is, an Oscar winning director or a filmmaker. Not everyone is a Christopher Nolan or a Steven Spielberg, right? But it has given us ways to consume content in different ways. It has enabled people to create things in new ways. It's enabled a better way for communication for all of us. It's created its own channel, which people have leveraged in different ways to create newer things, more creative things. So the way you need to think about tools that are up and coming, with caution, of course, is that they will open the way, revolutionize or a renaissance of sort in terms of how our thought processes evolved over time. And it is going to cause a drastic shift for sure, but it in no means can replace human thought and human creativity, because at the end of the day, these are all a product of our own creativity. With that, I hope you guys really enjoyed the session. And thank you.